All right, welcome back to AI Paper Podcast. Today we're cracking open BLIP3-0, a family of fully open, unified, multimodal models, architecture, training, and dataset. And for those tuning in, just for the quick summary, this paper introduces BLIP3-0. It's a new family of models, unified models. They're pretty good at both understanding and generating images. The key innovation here seems to be using a diffusion transformer to create these semantically rich syllab features. They found this helps with training efficiency and, well, just better image quality compared to the older VAE methods. Also really interesting is their finding on sequential training. Training understanding first, then generation seems to boost performance quite a bit. Plus, and this is big, they're releasing a new instruction tuning dataset, BLIP3-0 60K. They actually use GPT-4O to build it, and it apparently makes the model much better at generating tricky things like complex gestures or specific landmarks, even simple text. So yeah, BLIP3-0 hit state-of-the-art on a bunch of benchmarks and maybe the best part for our community. Everything models, code, weights, datasets, it's all fully open sourced.
Okay, let's dive a bit deeper now. We've got this paper from Salesforce Research and quite a few universities involved too. They're tackling a really core challenge. How do we actually build the best unified AI? One that can both see the world and, create images of it.
Exactly. And this whole push towards unified multimodal models, it's a really hot area right now. You see them referencing models like GPT-4O, which just shows how much interest there is. This research specifically is digging into the best architecture and, maybe more importantly, the best training recipe when you want one single model that handles understanding images and generating really high quality ones.
Yeah, it feels like for a while, maybe the focus was tilted more towards the understanding part of multimodal AI.
Mm-hmm.
This paper seems to really zero in on optimizing generation within that unified setup. And they've highlighted some key design choices to explore, right?
That's right. Things like how the model represents images internally, the actual data format.
And the objectives, the loss functions they use during training.
Yep. And the overall strategy, like do you train everything together or do you do it in stages?
And I got to say again, that open source commitment is fantastic. It just fuels more research, lets people reproduce results, build on it. That's huge for the field.
Absolutely huge. And maybe if we just step back for a second, think about why these unified models are so important. The potential is just immense. Imagine an AI that, you give it a complex description, maybe a cat wearing sunglasses, riding a unicycle on the moon, and it just gets it. It understands all those pieces and generates an image that actually matches without needing you to rephrase the prompt 10 times or switch between different tools.
Right, because it's leveraging that deep language understanding it already has from its pre-training.
Yeah.
It makes the whole process feel much more seamless.
Exactly. And then there's this idea of in-context learning for visual tasks. The paper talks about this, how these models can use what they've already generated, text or images, as context for the next step.
No, like iterative image editing. You could sort of chat with the AI to refine an image it made.
Precisely. Or step-by-step visual reasoning. Doing it all within one model. No more juggling different specialized AIs. It just removes a lot of friction.
Yeah, that makes sense.
Yeah.
And looking bigger picture towards like AGI.
Well, yeah, if you think about artificial general intelligence, this ability to fluidly perceive, interpret, and generate across different modes, text, images, maybe audio, video down the line, it feels pretty fundamental.
It's moving towards AI that interacts more like humans do, in a more holistic way.
I think that's a good way to put it, more intuitive interaction.
Okay, so let's get into the nitty-gritty. How are they actually combining these different model types? They mentioned autoregressive models and diffusion models, and they even nod to the buzz around GPT-4O, possibly using a hybrid approach. That idea of text tokens, autoregressive model, diffusion model, image pixels.
Yeah, they use that as a sort of jumping off point. This study really tries to systematically break down the key design choices within that kind of framework. They're essentially asking three main questions. First, what's the best internal image representation? Is it VAE latents or maybe CLIP embeddings?
Okay, VAEs versus CLIP.
Second, what's the best training objective? Good old mean squared error, or something more complex like flow matching.
MSE versus flow matching, got it.
And third, what's the best overall training strategy? Train everything jointly or do it sequentially, one step after the other.
Let's unpack that first one, image encoding and reconstruction, VAEs versus CLIP plus diffusion. How do those stack up?
Okay, so variational autoencoders, VAEs, they're pretty standard, right? They compress an image into a structured latent space, sort of compact code. Then a decoder tries to rebuild the image from that code.
And that's what a lot of latent diffusion models use under the hood for efficiency.
Exactly. They generally give you good reconstruction quality, they're well understood, a solid baseline.
Okay, so what about the alternative? Using CLIP.
Right, so CLIP is fantastic at understanding the semantics of an image, its meaning, because of how it's trained on image-text pairs. But it wasn't built to reconstruct images pixel by pixel.
So how do they use it for generation then?
The approach, which we've seen in other models like EMU2, is to pair the CLIP encoder with a diffusion decoder. The CLIP encoder pulls out these high-level semantic features, in their case, 64 continuous vectors. Then they train a diffusion model, separate from CLIP, to take those semantic CLIP embeddings and generate the actual image pixels.
Ah, okay, so CLIP provides the what, and the diffusion decoder figures out the how to draw it.
Pretty much, and an important detail. Although it's a diffusion architecture for the decoder, once it's trained, it actually runs deterministically during generation, based on whatever CLIP features the main model predicts.
Interesting. So what's the trade-off then? VAE seems maybe better for perfect reconstruction?
Potentially, yeah, for pixel perfect reconstruction.
Yeah.
But the CLI diffusion approach has this big advantage in compression and the kind of information it captures. These CLIP embeddings are fixed length, which is computationally nice, especially for higher res images. And crucially, they're packed with semantic meaning, the essence of the image, not just pixel patterns.
So VAE is maybe more about the look, CLIP is more about the meaning?
That's a decent simplification, yeah. CLIP gives you a very compact, semantically rich representation, which turns out to be really useful for guiding generation from text.
Oh, so once you have these image representations, these embeddings, how does the model learn to generate them from a text prompt? You mentioned an autoregressive model.
Right, so the text prompt goes in, gets encoded, then they add this special learnable query vector. This query is trained to kind of look at the encoded prompt and figure out what the target image feature should be, whether it's the VAE feature or the CLIP feature.
And that's where the training objective comes in, MSE or flow matching?
Exactly. MSE, mean squared error, is the straightforward one. Just measure the difference between the predicted feature and the real one and try to minimize that difference. Simple, computationally cheap.
But what's the downside?
The main issue they point out is that MSE tends to push the model towards predicting a kind of average feature. It makes the output very deterministic. Give it the same prompt, you'll likely get almost the same image embedding every time.
Which means less variety in the generated images.
Precisely. You lose diversity. That's where flow matching comes into play.
Okay, how does that work? Sounds more complex.
It is a bit more involved. Instead of just predicting one point, flow matching tries to model the whole probability distribution of the image features. It learns a sort of velocity field that can guide random noise towards the correct feature representation over a continuous time path.
Whoa, okay. So it learns a process, not just an endpoint.
Kind of, yeah. And the big benefit is that during inference, you can introduce randomness into that process, stochastic sampling. This lets you generate many different diverse images that are all consistent with the same text prompt.
So that's how you get variety. But I guess it's harder to train.
It increases the model complexity for sure. They use a diffusion transformer, like a DIT variant, for this flow matching part, which is a more sophisticated architecture than just predicting a vector and calculating MSE.
Okay, so summarizing the design choices they tested. It was CLIP embeddings plus MSE loss.
Yep, inspired by models like EMU2.
Then CLIP embeddings plus flow matching.
Right, using that diffusion transformer to predict the CLIP features.
And finally, VAE latents plus flow matching.
Similar to another model called MetaQuery, and they deliberately skipped VAE plus MSE because they were focused on this autoregressive plus diffusion setup.
Gotcha. And when they ran the experiments, using metrics like FID for quality and GenUL, DPG bench for prompt alignment, what did they find?
The results are pretty interesting. The CLIP plus flow matching combo generally scored best on prompt alignment. The images matched the text descriptions most closely.
Okay, so CLIP's semantics plus flow matching's distribution modeling really helped there.
Seems so. Now, VAE plus flow matching actually got the best FID score, which usually indicates better visual or aesthetic quality.
But FID isn't perfect, right?
Exactly. The authors themselves mention the limitations, even pointing out GPT-4's relatively high FID. So while VAEs might produce aesthetically pleasing outputs according to FID, the CLIP plus flow matching seemed better overall at capturing the prompt's intent and generating diverse results. That's the one they identified as the most effective design.
And the key takeaways from this comparison were:
Two main things, really. First, for these unified models generating images, the autoregressive part seems better at learning and predicting high-level semantic features like CLIPs compared to lower-level pixel features from VAEs.
Makes sense. Easier to connect text meaning to image meaning.
And second, flow matching, despite its complexity, seems superior to MSE for capturing the true distribution of images, leading to more diversity and better visual quality overall.
Okay, so that solidifies their choice of CLIP plus flow matching. Now, how did they approach actually training the whole unified model? Joint versus sequential.
Right, so the challenge is integrating the image understanding and image generation parts, especially since they decided both should operate in that CLIP embedding space.
So joint training that's throwing everything in together. Understanding data, generation data, train it all at once.
Yeah, models like Metamorph did that. The hope is you get synergy shared learning. But the paper notes, it can be tricky. Success really depends on having massive amounts of data and getting the ratio between understanding and generation data just right. It's a balancing act.
And the alternative is sequential training. Stage 1, stage 2.
Exactly. Stage 1, train the model, or at least the backbone, just for image understanding. Stage 2, freeze that understanding part, and then train only the image generation components.
Like LM Fusion and MetaQuery did.
Right. And the big advantage they highlight for sequential is flexibility. You lock in the understanding performance, and then you can focus all your resources on making the generation really good without worrying about messing up the understanding part.
Less interference between the tasks.
Pretty much. And that's the route they chose for BLIP3-0.
Which brings us to BLIP3-0 itself. Built using CLIP plus flow matching, trained sequentially. And they have two versions.
Yep, an 8 billion parameter one using some proprietary data alongside open data, and a 4 billion parameter one that's trained only on open source data.
And for the understanding part, they kind of took a shortcut.
A strategic one, yeah. They recognize how good some open source vision language models like Qwen 2.5 VL already are. So instead of training understanding from scratch, they just took a pre-trained Qwen model, froze it, and built their generation module on top.
Smart. Leverage the best available components. So for the 8B BLIP3-0, they froze the Qwen 2.5 VL7B instruct.
And then trained their diffusion transformer for generation, which was still about 1.4 billion parameters. The 4B model used a smaller Qwen backbone, the 3B one.
And the architecture for that diffusion transformer.
It's based on something called Lumina Next, which improves on NextIT. They mention using fancy techniques like 3D rotary position embedding, sandwich normalization, grouped query attention. Basically, modern transformer tricks for efficiency and stability. Helps get better images with fewer artifacts.
Okay, let's talk training data for generation. Stage 1 pre-training.
For the 8B model, it was around 25 million open source images. CC12M, SA1B, JourneyDB, plus another 30 million proprietary ones. Crucially, the captions weren't just the original short ones. They used the powerful Qwen model itself to generate detailed captions, averaging like 120 tokens.
Wow, okay, so much richer text to learn from.
Exactly. Though they did mix in about 10% shorter captions too, just to make sure it could handle prompts of different lengths. The 4B model used just the 25 million public images, but with those same detailed and short captions.
And they're releasing those captions?
Yes, the 25 million detailed ones and 3 million short ones. A great resource for the community.
Okay, then stage 2, instruction tuning. Why was this needed?
They found the pre-trained model still struggled with certain things, complex human gestures like specific hand signs maybe, common objects sometimes weren't quite right, landmarks, and especially rendering text within images.
Which are all known hard problems for image generation models.
Definitely. So to fix this, they cleverly used GPT-4O. They prompted it to create about 10,000 image prompt pairs specifically targeting each of those weak areas.
Using AI to teach AI.
Pretty much. They also added more prompts from JourneyDB and DLE3 to boost the overall visual aesthetics. This resulted in their BLIP3-0 60K dataset, which, again, they're releasing.
And did this instruction tuning actually work?
Massively, according to the paper. It significantly improved prompt alignment, getting those tricky details right, and also boosted the visual quality, cutting down on weird artifacts.
And the benchmark results reflect this.
They do. For image understanding, the 8B model is state-of-the-art on most standard benchmarks. Table 1 in the paper lays it all out.
And for generation.
Strong performance on metrics like Geneval and WISE, showing good prompt following and world knowledge. It's scored lower on DPG Bench, but they question that metric's reliability. The key thing was the clear jump in quality after the BLIP3-0 60K tuning.
Did they do any human evaluation? Sometimes the numbers don't tell the whole story.
They did. They compared BLIP3-0 head-to-head with another model, Janus Pro, using human annotators. Even though Janus Pro scored higher on that questionable DPG bench metric, the humans significantly preferred BLIP3 images for both visual quality and how well they matched the prompt.
That's pretty convincing. Human preference often cuts through the metric noise.
Right. And another interesting finding was how quickly the model seemed to pick up the style of the GPT-4O generated data during instruction tuning. It suggests high-quality synthetic data can be a really powerful training signal.
So what's next for BLIP3? Where do they see this going?
They're already looking at extending it to downstream tasks, things like image editing based on instructions, multi-turn visual conversations.
Oh, cool. Like, make this guy in that picture you just generated a bit more red.
Exactly, and also interleaved generation, mixing text and images in a continuous output. Their first step seems to be just getting basic image reconstruction working well, feeding an image in and getting back out through the whole understand then generate pipeline. And they mentioned needing more instruction tuning data tailored for these specific applications.
Makes sense. The model needs examples of how to perform those specific tasks.
Yeah. And they also position their work relative to others, acknowledging models like CDEX, EMU2, Chameleon, Janus, etc. They argue BLIP3-0 is the first really systematic look at this specific autoregressive plus diffusion framework using CLI-Pay and flow matching.
Okay, so wrapping it all up, this paper really dug deep into designing and training these unified models.
Absolutely. A systematic exploration.
Key takeaways seem to be CLIP embeddings plus flow matching is a winning combo for generation in this setup.
Right. Better semantics, better diversity.
Sequential training offers critical flexibility over joint training, letting you optimize understanding and generation separately.
Isolates the stages.
And targeted instruction tuning, potentially even using powerful models like GPT-4O to create the data, can significantly patch up weaknesses and boost overall quality. That BLIP3-0 60K dataset sounds really valuable.
Definitely. And achieving state-of-the-art results on top of that is impressive.
And I think we have to underline it again. The commitment to open sourcing everything, the models, the code, the training scripts, the new data sets, that's just fantastic for the research community.
It really is. It lowers the barrier for entry, allows for verification, and just accelerates progress for everyone building on this work.
For sure. It's exciting to think where this leads next. Better image editing, real visual dialogue. Really makes you wonder, doesn't it? With models like BLIP3-0 becoming open and accessible, what completely new applications or creative tools might pop up that we haven't even thought of yet? How fast will this open approach drive innovation?
That's the million-dollar question, isn't it? It feels like we're just scratching the surface of what these truly unified multimodal systems can do.